Autophagy is supposed to happen when food disappears, but beans create a strange overlap with fasting biology. You can eat a full meal, calories, carbs, and protein included, while turning down one of the same nutrient signals fasting shuts off. The reason is not fiber, and it is not blood sugar. It is one amino acid, methionine. And your cells are surprisingly sensitive to how much of it arrives, which means the plate can still be full, while part of the cell starts hearing scarcity. So how can food send a signal that normally belongs to fasting? Most people picture autophagy like a stopwatch. Do not eat for 12 hours, 16, 24. Then, at some magical moment, the cell suddenly starts cleaning itself. But cells do not own stopwatches. They own sensors. One of the systems behind that decision is a nutrient-sensitive growth switch called mTORC1. From here on, think of it simply as the growth switch. When nutrients are abundant, the growth switch stays active. Build proteins, make structures, use the material coming in. When nutrient signals fall, the growth switch becomes quieter, and one of the brakes holding autophagy back begins to loosen. That is part of what fasting does. But here is the first reversal. The growth switch does not simply ask, "Did you eat?" It asks, "What arrived?" Especially which amino acids arrived. So two meals can both contain calories, both contain protein, and still look very different from inside the cell. Fed versus fasted is not a perfect on-off switch. The molecular message inside the meal matters too. Methionine is where the meal becomes a message. Methionine is an essential amino acid. Essential means your body cannot make enough of it on its own, so it has to come from food. Your body needs methionine to build proteins and to make other molecules that support normal cell chemistry, growth, and repair. One of those molecules is SAM, short for S-adenosylmethionine. You only need to remember what SAM means. It is the cell's methionine signal. High SAM says, "Methionine is here. Keep building." Low SAM says something different. The cell even has a dedicated sensor for that signal, called SAMTOR. When the methionine signal falls, the sensor notices, and the growth switch becomes quieter. And when the growth switch becomes quieter, one of the brakes on cellular recycling begins to loosen. That is the key idea. Fasting is one way to create nutrient scarcity, but it is not the only way to change a scarcity signal. You can also change the message by changing which nutrients arrive. The plate can be full while one important growth signal is being turned down. So why would beans change that signal at all? Because bean protein carries a different amino acid pattern. Black beans, kidney beans, pinto beans, and white beans all contain protein. But compared with many animal proteins, common beans tend to deliver less methionine relative to their total protein. Human tracer work with pinto beans has identified methionine as one of the amino acids that limits that protein. Broader comparisons between plant and animal proteins show the same general pattern. Many plant proteins carry less methionine relative to their total protein. But the important part is not the study name or the protein score. It is what that means inside the cell. Two meals can show a similar number of protein grams on a nutrition label, while delivering a very different methionine signal. That does not make animal protein bad, and it does not make methionine the enemy. It simply means beans speak a different amino acid language, and there is no convincing evidence that black beans are some special autophagy bean, while kidney or white beans are not. The bigger difference is not the color of the bean. It is how the beans change the amino acid pattern of the whole meal. Now comes the test that matters. If methionine really changes nutrient sensing, then lowering it should change the body's scarcity response even when people keep eating. And controlled human feeding studies show that the body notices. Within days, lowering the methionine and related amino acids changed hormones and metabolic signals that rise when the body senses amino acid scarcity. No one was fasting. Food kept coming in, yet the body was responding as though one important nutrient had become harder to find. That is the conclusion that matters. Removing calories is not the only way to create a scarcity signal. Fasting turns down almost the entire nutrient orchestra. Changing the amino acid pattern can quiet one instrument while the music is still playing. Methionine. And this is where most people would accidentally undo the whole idea. If you eat the beans next to the steak, you may miss the mechanism. Imagine two dinners. Dinner 1, a large serving of meat plus half a cup of beans on the side. Dinner 2, beans replace a meaningful part of that meat. Both dinners contain beans, but only one clearly changes the amino acid pattern of the meal in the direction we are talking about. Your cells do not award points for eating a healthy bean. They only see the molecules that arrived. So if the mechanism is methionine sensing, replacement matters more than addition. That changes the practical question completely. Do not ask only, how many beans did I eat? Ask, what did the beans replace? Because the biology is not attached to the word beans. It is attached to the signal the whole meal creates. There is another molecule hiding in the same bowl, spermidine. And yes, the name sounds suspiciously close to sperm. But spermidine itself is not some special sperm molecule. Your cells make it throughout the body, where it helps regulate cellular maintenance and recycling. And the funny part is, the name is not random either. It traces back to the early discovery of these molecules in semen. But what makes it interesting here has nothing to do with reproduction. It has to do with what happens when you stop eating. During fasting, spermidine begins to rise. In one human group, levels increased by roughly 50% after 4 to 5 days. That could have made spermidine just another marker of fasting. Then scientists blocked cells from making it. The fasting-induced recycling response weakened. So spermidine was not simply watching the fast happen. It was helping the response happen. And now look back at the bowl. Beans naturally contain spermidine. That gives beans a second connection to fasting biology, different from methionine, but pointing toward the same cellular recycling system. Methionine changes the nutrient signal. Spermidine adds a second mechanistic connection to the recycling machinery. Methionine is still the main secret in this story. It is just not the only connection. No. And pretending they are would miss what makes this interesting. Fasting changes far more than methionine. Insulin falls. Energy availability changes. Multiple amino acids decline. Several nutrient and energy sensors shift together. Beans do not reproduce that entire state. What they reveal is something more useful. The body does not divide the world into only two categories, eating and fasting. Cells read a network of signals. Fasting changes many of them at once. Food can change some of them selectively. So beans are not a secret fast. They are a way of changing part of the fasting message while still eating. That distinction is the whole story. This is where the science refuses to give us a magic number. There is no human trial showing that half a cup, 1 cup, or 2 cups of beans creates a defined increase in autophagy. So there is no proven autophagy dose of beans. A bowl of cooked beans, roughly a cup, can simply be enough to make beans the meaningful protein base of a meal. That is a practical serving, not a proven biological threshold. And frequency works the same way. One bean meal is not a fasting protocol. The more biologically coherent pattern is regular substitution. Beans replacing part of a higher methionine protein source, often enough to change the amino acid pattern of the diet. Think meal architecture, not a bean dose. And whether the bowl contains black, kidney, pinto, or white beans probably matters less than that substitution itself. There is one more reason not to turn methionine into the villain. Remember, methionine is essential. The body still needs it. That is why the goal is not to eliminate methionine. It is to understand what changes when the signal becomes lower. And more autophagy is not automatically better. Cells need both modes: build, repair, grow, recycle. The goal is not to drive methionine towards zero. The lesson is that the switch is more sensitive than fed versus fasted. Fasting and beans are not the same. Fasting shuts down almost the entire incoming nutrient message. Beans do something narrower, but surprisingly important. They can change part of that message while the meal is still on the plate. Less methionine means less pressure on the cell's growth switch. Spermidine adds a second connection to the machinery of cellular recycling. And that is why the most important question is not simply, did I eat beans? It is, what did the beans replace? Because your cells do not read foods as healthy or unhealthy. They read signals. Fasting empties the plate. Beans change what the plate tells the cell. That is the methionine secret.